Thank you for your invitation. Thank you for your introduction. Actually, you already said 70% of my talk. So today I will speak about the Earth, and more specifically a region of the Earth which we call the deep mantle, and which is located approximately 2,000 to 3,000 kilometers below our feet. And by the end of the talk, I will try to show a few slides about another activity that I have, and which is to model the evolution of icy bodies like Europa. Yeah, I show Pluto because I like this picture. The title of this talk is The Geographer and the Astronomer, but before introducing these two persons, I would like to say a few things about how do we guess or infer the structure of the deep mantle and of planetary interior. So I put these slides. I think you all know about the radial structure of the Earth, that the Earth is differentiated into an inner core, which is a solid iron, about 1,200 kilometers in radius. And then around this, you have the outer core, also iron, but liquid. That's where the magnetic field is generated. And here we have the core mantle boundary at about 3,480 kilometers. And then comes the mantle, which we separate into entities or in two parts, the lower mantle, down to 700 kilometers below our feet, and the upper mantle. I mean, the difference is only, let's say, is only the kind of minerals that you can find it, and it is triggered only by change in the pressure. And only at the top here we have 20 kilometers of crust. So you probably all know this, or at least you learned this during at school. And you can see also on this picture some other structure, plumes or even super plumes, which are actually some odd currents or odd material rising from the core mantle boundary up to the surface. And the other way around, you see some what we call slabs, which are actually downwelling currents, downwelling cold currents, which originate at subduction zones and which sink through the mantle. So now what we would like to know, what we would like to understand is what is the lateral structure or the 3D structure of the Earth, and how do we relate this to dynamics. So this is basically what people studying the interior of the Earth or the mantle are doing. So to do this, we can rely on one main observation, which is seismic tomography. I will come back to this during the talk. And we can relate seismic tomography, which is actually some anomalies in seismic velocities, to the thermochemical structure. To do this, we need some mineral physics data, which is not always easy, because, of course, you can get some uncertainties and you don't get always exactly the data you need. But it works quite well. We can also add some isotope geochemistry data. Isotope geochemistry gives you some hints about the evolution of the mantle. And we can add some other constraints. Actually, since a few years, we start to try to see if we can use other constraints, including the core mantle boundary topography, seismic attenuation, and more data. And today I will more focus on these two items. And of course, on the other side, we can get some important information by doing some numerical modeling, and more specifically, numerical modeling or solid convection. We think that we are sure even that the Earth mantle is animated by convection. So if we simulate convection using some computers, for instance, then it's possible to reconstruct some structures which we can compare to what we observe, that is to say, seismic tomography. Let's jump to the thermal evolution of planets and moons. So you also probably all know that all the planets, the moons, have started hot. They stored some energy during their formation. They also have some energy in the form of radioactive elements. And of course, they have to release this energy towards space. This is the second law of thermodynamics. And the best proof of this is volcanism. One thing that probes have seen when we explore the solar system is volcanoes everywhere. Some are probably extinct, like the volcanoes on Mars, but some are obviously active, like on Earth, Io. And more recently, we also discovered what we call cryovolcanism, which is related to sort of activities in the icy moons of solar system. So, of course, if these bodies are cooling, we can ask the question about how do they do this and how efficient is the cooling. So, the heat transfer through rocky mantles, like in the Earth and Mars, etc. And the outer shell can be done in basically two ways, either convection or by conduction. And it turns out that the properties of these mantles and icy shells are such that convection, solid-state convection, can happen within them, can operate within them. So as you see, one central activity in understanding the dynamics and structure of planetary mantles is convection, modeling convection. Just to define this very briefly, convection is a mode of heat transfer by advection of mass. And it is driven by lateral anomalies in density. Of course, at the end, this is gravity. But you need to have some lateral anomalies or lateral changes in density to drive convection. Let's see how can we do this with a very simple example, which is a Rayleigh-Bénard convection. In this case, you put a fluid in between two surfaces, a hot surface at the bottom and a cool surface at the top. So the fluid is heating from the bottom and is cooling at the top. In that case, what you generate is hot plumes or ascending currents here and cold downwellings or cold slab, which are actually being generated by instabilities that are growing in these two regions, which we call thermal boundary layers. Now, of course, this is a more simple system you can imagine for convection. And there are much more complexities in natural systems, including, first of all, the shape. The planets are spheres. Another complexity is the mode of heating. In that case, there is only basal heating, but if you have some radiogenic elements, like in the Earth's mantle, you also should take into account internal heating. And finally, the rheology, that is to say, the way rocks are deforming. This one is a very also important aspect. So I would like to illustrate this only with two slides. Oh, first of all, a bit more detail about convection, since you asked the question. How do we model convection numerically? So we need three equations, three conservation equations, conservation of mass. Here it is written for incompressible fluid, but we also do some simulation for compressible fluids. The second thing is a momentum equation. And there is a very important simplification in the case of the Earth's mantle, is that the acceleration, which is here, is much lower than the stretch divergence. I mean, it scales at density times diffusivity divided by viscosity. And the viscosity is so high that this term here is very small, which means we can eliminate the acceleration, which makes things much easier to calculate. The second thing is you need some constitutive equation to relate the stress here to the strain rate here. And the important parameter here is the viscosity, which is appearing here. So remind that the stress depends on viscosity, and viscosity can vary a lot, in particular with temperature. And the fourth equation, of course, is the conservation of energy, which simply describes the variation of temperature as a function of different terms, conductive term, advective terms, and some source term, in which we include, of course, radiogenic heating, internal heating, if there is. In the case of thermochemical convection, that is to say, you also assume that you have some material of different chemistry, so with different density. You also you have to add some equation expressing the conservation of the composition. Okay, now I would like to illustrate the effect of two important parameters which I already mentioned, the effect of internal heating. These are two lines of, or two series of experiments for two different geometry or two different core size, here and here. And if you go from the left to the right, we progressively increase the amount of internal heating within the system. Here there is no internal heating, and here there is a very strong internal heating. And what you see here is that the plumes, which you see here, are progressively weakening as you increase the amount of internal energy. That is to say, the plumes do not reach the surface. In this case here, there is even no more plumes. And the system is dynamically controlled only by downwellings, which you can see here and here. So the system is heating up, and no more plumes if you put inside the system too much energy, too much heating. The second thing I would like to illustrate here is the effect of viscosity variation with temperature. This is very important. If these variations are strong enough, what's going to happen is that because the top part is colder than the bottom part, the top part of the fluid will also be much more viscous. And in that case, we end up with a mode of convection which we call stagnant lead convection or rigid lead convection, in which a stagnant lead, where heat is transported by conduction, is forming at the top of the fluid. And you can see it here. It's materialized with this blue isosurface. By the way, here what I show is the temperature. I forgot to mention this, non-dimensional temperature. And you can see again that the plumes here do not reach the surface, but are just stopped below the stagnant lead. So one consequence of this is that the heat transfer, of course, is strongly reduced when you have this kind of system. Okay, it's time now to introduce the Geographer. It's a painting by Vermeer, Dutch painter. And at the time Vermeer painted this painting, or made this painting, the European people were starting to make trade all around the world. And to do this, of course, they needed some maps as precise as possible. And that was the job of a geographer. The reason I put this painting is not only because it is beautiful. It is also to say that, in a way, what geophysicists studying the mantle today are trying to do the same thing, except that we don't want to trade with people in deep mantle. But we are trying to establish some maps of the Earth's mantle. We are trying to understand what is the structure of the mantle. And it turned out that we do have such maps. We call this seismic tomography. I will explain after this slide what it is exactly. But typically, these are some anomalies of the seismic velocities compared to some average. And by convention, the red parts here are regions where seismic velocity travels slower than average. And the blue part are regions where seismic velocity travels faster than average. And like this, we can build some map. Each column here is a different model built in the past 20 years or something like this. And each line represents a depth from 100 kilometers to 2,800 kilometers, so bottom of the mountain. And what do we see here is that basically we start to have some sort of consensus on the big structure, the large-scale structure of the mantle. We see that where do we find some strong heterogeneities? Well, typically between the surface down to 300-400 kilometers. And these structures are somehow mimicking the plate tectonics. That is to say, you see blue structure, so fast structure beneath continents, and hot structure along mid-oceanic ridges. I'm not going to talk about this anymore today, but I would like to go to the bottom of the mantle where we see, again, some very strong seismic velocity anomalies. And they are distributed here in basically two big regions, which I will introduce later, which we call low shear-wave velocity provinces, one below the Pacific and the other one below Africa. So just two slides about seismology. You also probably know this, that within the Earth, to a first approximation, you can consider that at short time scale, the Earth's mantle is elastic. And so elastic wave can propagate through it. And that's the case of seismic waves, in particular the compressional waves and the shear wave. Compressional waves here are illustrated on this column here. If you imagine a small block, which is not perturbed, a compressional wave or P wave will correspond to successive compression and dilatation of the medium. And these perturbations are along the direction of propagation, which in this case is in that direction, or if you want, perpendicular to the wavefront. The other mode of perturbation, or the other main seismic phase, is a S, or shear wave, or secondary wave, if you want. And in that case, the perturbation is perpendicular to the direction of propagation, or parallel to the wavefront, if you want. So, of course, these waves travel with different velocities in different medium. P wave is always faster than S wave. And the key thing here is that they are traveling with different velocity depending on temperature, composition, etc. Now imagine that we can observe some seismic rays going through all around throughout the Earth. We have, for instance, one ray here going from one earthquake to one seismometer, another one here, etc., etc. So when they travel through the Earth, the rays are sampling different regions. For instance, these big blue blobs here, which maybe is colder than average or made of some different material. And the idea behind seismic tomography is that is to measure either the waveform anomaly or the travel time anomaly of seismic wave at all these stations here, and to invert this travel time for a model of structure. That is to say, at each box here in this at each point of the Earth, or if you want, each box of the parameterization model, we calculate one value for the seismic velocity anomaly. Most of the time Vs, because for, that is to say, shear velocity, because for compressional velocity it's a bit more difficult. So if we have data at all these points, from all these earthquakes, in principle it's possible to get some maps of shear velocity anomalies like those I've shown at the beginning, in the previous slides. Of course, it's much more difficult than this because, as you know, the earthquakes don't happen everywhere. Well, we have a lot here in Taiwan, but for instance, where I come from in France, there is no earthquake or very few. And we cannot put seismometers everywhere for a lot of reasons, political reasons, geographical reasons. So the problem is much more difficult to solve than what I'm saying now, but I'm, of course, not going into the details of this. Back to the bottom of the mantle, I want to say a few words about these regions here, which we call low shear-wave velocity provinces. Typically, they have the size of continents, about 5,000 kilometers across, and within this region, the shear seismic velocity decreased by a few percent, 2-3%, depending on the model, compared to the average in these depths. 2 or 3% is a lot for in seismology. And they extend from the CMB upward in the mantle to altitude of 500 to 600 kilometers. Oh, by the way, if there is some cosmologists in the room, they may wonder what the cosmic microwave background has to do with the Earth. It's my fault, I'm sorry. CMB is not a cosmic microwave background, it's called mantle boundary. If you meet geophysicists in the future, now you know. Anyway, that's what I wanted to say about these low shear velocity province. One important thing is that we see it on all models of tomography that we have built so far. Actually, the most recent models show that they are more looking like bundles with some holes inside, but they are still present. So these are robust features. That's the message I want to give. Okay, how do we try to understand what causes these anomalies? Seismic velocity anomalies can be related to elastic modulus, the bulk modulus, okay, and the shear modulus, or rigidity, G, of mantle materials, and of course to the density. So with this, we can try to reconstruct, we can try to make some hypotheses about what caused the anomalies in the deep mantle. The reason is that, of course, density and elastic moduli are themselves depending on temperature, pressure, and on the composition. For instance, the temperature, if you increase the temperature, density, elastic moduli are decreasing. And VS is shear velocity, and VP is compressional velocity. Both velocities are decreasing. So when you see some red on the maps I've shown, it could be simply that the temperature is increasing. Another element which is important is the iron content. When I say iron, it's actually iron oxide, FeO. If you increase the iron content, then the density on the bulk modulus are increasing. But, and this is very important for the end of the story, for the rest of the story, the shear modulus is decreasing. Something, I will only say one more of this, I will not go into the detail, but what do we need to calculate the density and the thermoelastic properties of the mantle aggregate? You know that the mantle is not one single crystal, it's different crystals which are forming some rocks, and the different crystals have different densities and different elastic modulus. So what we do is that we get some information from mineral physics, either experimental or ab initio calculation, and this gives us values of density and elastic moduli for each minerals. And then we have to do, of course, some extrapolation at high pressure, high temperature, because the experiments usually in mineral physics are done at high pressure but at low temperature. And for this, we use usually Birch-Monaghan equation of state. And then we have some specific average scheme to calculate the density and elastic moduli of the rocks. Now, what can be the possible sources for the seismic anomalies we have introduced? Of course, temperature anomaly, I mentioned this already. You know that there are plumes, they are hot, so in principle they will appear in red, slow velocity. And we have slabs which are on the contrary colder. So they go down, they are colder, so they will appear in blue, colder than, slower than average. And we see this in thermal boundary layers. And you remember thermal boundary layers, there is one at the bottom, one at the top. You have large variation of temperature in this one. So, it's exactly what we see in seismic tomography. So maybe temperature is, to the first order, a good explanation. But it turns out that also that the mantle is a bit more complicated from the mineralogical point of view, and in particular the lower mantle. It's composed on two main minerals. There are others, but the two main minerals are what we call the bridgemanite, with this formula. It's basically iron, magnesium, and silicate oxide, and ferropericlase, which is magnesium and iron oxide. We define also an average rock, which we call parallite. So a paralitic composition means about 80% of bridgemanite with about 10% of iron oxide. So some obvious candidates for these seismic velocity anomalies are changes in the relative fraction in bridgemanite and ferropericlase, because they have different properties, and or some variation in the fraction of iron, in particular iron oxides. And I mentioned that the iron oxide have some very interesting properties in terms of elastic moduli, for instance. There are more complications. Since about 2 decades, we know that At the very bottom of the mantle, this mineral is transforming to a high pressure phase, which we call post-perovskite. And the Clapeyron slope of this phase transformation is very high, which means very sensitive to temperature. So whenever you have some lateral variation in temperature, the topography of this phase transition will vary a lot. And of course, because the post-perovskite, seismic velocity travels differently in post-perovskite and in bitumenite, this can trigger some anomalies in seismic velocity. And there are more. The slabs, which I showed on a previous picture, they are mainly made of old oceanic crust, which has a different composition than the rest of the mantle. So when you bring this to the lower mantle, you create some anomalies. And it can be some melt, presence of water or other fluids. So there can be many different sources for these anomalies. So just a picture at this stage to ask the question, what do we see? What are these low shear-wave velocity province? Is it some sort of plume cluster like this? So purely thermal hypothesis or purely thermal structure? Or do we have some thermochemical structure with some piles which are simultaneously hotter and with a different composition than the rest of the mantle, and with maybe different variation of this plume, some very stable piles or metastable piles, or on the contrary, some big domes, which is increasing. So this is the question we try to answer. Basically, do we have plumes or do we have some thermochemical piles? By thermochemical piles, I mean something which is hotter and made of a slightly different material than the rest of the mantle. First question is, this model here, or this explanation, is it possible to do this dynamically? So for this, we need to do some model of convection. And by doing not only some purely thermal convection, but also adding some chemical convection. So because that thermochemical convection. And the way we do this is usually to set up a system with a layer of dense material at the bottom, and we see how this is evolving. This is just one example, which is one of my models, but other people have done this again. And the main question is it dynamically feasible? The answer is yes. And the important parameter here is the density contrast between the dense material that you set up at the bottom of the mantle and the rest of the mantle. So here I show one model. Here you have the temperature, ideal surface, and here a slice of the temperature, and here same thing for the composition. And we clearly see that it's possible to maintain an initial layer of dense material at the bottom, which is represented here in white, and which can remain stable for a very long period of time. And in addition to this, if you draw some maps of or some spectral heterogeneity maps or some spectrum of this heterogeneity, you see that you can create here some very strong anomalies, lateral anomalies, with here, of course, they are dominated by low degrees 2 to 4, but these anomalies can be the source of the seismic velocity anomaly we see. Okay, now how can we decide if it is purely thermal or thermochemical? If we only have shear wave velocity, which is the case so far, it's very difficult. The reason is that shear wave velocity is sensitive to both temperature and iron. So typically, if you draw a plot where you calculate shear wave velocity as a function of temperature and iron, you get something like this. The color code shows the temperature, the seismic velocity anomalies. Here as a function of temperature and the fraction of iron. So let's say, okay, I observe some 2% decrease in seismic velocity, minus 2%. What can it be? Minus 2% here, you see, is here. So basically, it can be a purely thermal anomaly here with some temperature change of about 800 K. But it could be also some increase in iron by 3% and some temperature increase of only 400 K. Which one to choose? I don't know. There is a full trade-off between composition and temperature, and there is no way I can decide between these two solutions, or any solution on this line. So this means we need some other type of data. And one possible type of data we can get is, I mentioned this already, is compositional wave. It's more difficult to build some tomographic map of compositional wave, but we can do it. On this plot here, I'm not showing the P-wave maps, but I show maps of what we call Bergson velocity. Bergson velocity is not something we observe. We just get the shear-wave velocity, or the shear-wave velocity and the compositional velocity. We combine them like this, and we get what we call Bergson velocity. And it is represented here. Maybe I should say why we do this is that it's very easy, is that the Bergson velocity depends only on the bulk modulus, while the compressional velocity depends both on bulk and shear modulus. So when we do this, there is something very interesting which is happening here at the bottom of the mantle. You recognize here the low shear velocity provinces, and if you look at the Bergson velocity, you see that it's not negative anomalies, that is, you don't have decrease in shear velocity in Bergson velocity, but you have an increase in Bergson velocity. And this, the fact that you get an anti-correlation between these two guys, it shows that it's not possible to have a purely thermal hypothesis. Otherwise, Bergson velocity would also appear here as red. So we could stop the talk here and say, well, we have anti-correlation between Vs and Bergson velocity, so this strongly supports thermochemical structure. I believe that's a very strong argument. But some other people came and said, oh, wait a minute. You know, we also have the post-perovskite, and it turns out that the post-perovskite, within post-perovskite, the shear velocity travels a bit faster, which means that if you have post-perovskite all around the mantle, all around the low shear velocity provinces, and no post-perovskite within the low shear velocity provinces, it's possible to get anti-correlation between shear velocity and the Bergson velocity. So again, we need some other constraint, additional constraint. I've listed a bit here. Geochemistry is important, and actually it also points toward, I will not detail this, only if you have questions later. Geochemistry is important, and it points to, again, thermochemical structure. The normal modes of the Earth, which are free oscillation of the Earth, allow to constrain the density. It's a bit controversial because the normal modes are how to say, interacting with each other, which induce some bias. But typically, we can get some density from this. And again, it supports some heavier low shear velocity province, which means chemical and thermal origin for these regions. But today, I would say only a few things about these two other constraint, which is dynamic topography at the core mantle boundary and the seismic attenuation. The dynamic topography, so the core mantle boundary has some topography, and it can be estimated by seismology, although it's very difficult. Actually, we don't have real model or some accurate model of the core mantle boundary. What is more easy to do is to predict what dynamically what this topography should be. The reason is that if you assume that you have dynamic topography, of course, it's strongly related to the dynamics. If you have some plumes here, for instance, the stress at the core mantle boundary will somehow stretch the boundary upwards, and you will create some positive topography, some upward topography. Yeah. If you have some slab or some downwellings arriving on this topography, it's the other way around. That is to say, you create some stress downwards, and it will induce some depression here. So now the question is, these famous thermochemical piles, what signature in terms of dynamic topography do they induce? So again, we have to do some modeling. This is not the same model I've shown earlier, but it's a similar one. And you can still observe that in this case, we can create some reservoir or piles of dense and hot materials here, with an antipodal position, which is interesting. And we do this for some value of the density contrast, which is about 140 kilogram per cubic meter. Now, the dynamic topography, we can calculate this from the normal stress, as I mentioned, at the core mantle boundary. And it is represented here with this color code. So blue is negative topography. You have some bumps or some depression in a CMB. And brown, you have some hills or some bumps in the CMB upwards. And in that case, we clearly see that this big reservoir here are creating some topography of about 1 to 2 kilometers deep, some depression 1 to 2 kilometers deep in the core mantle boundary. You can also see this very deep depression or deeper depression, about 10 kilometers or on average. And these ones are corresponding to slabs which are arriving at the bottom of the mountain. So potentially this is very interesting, because if you have forests of plumes, or if you have only plumes, you will have some positive topography. If you have some heavy piles like this, heavy and hot piles like this, then you create some depression. It's a bit more complicated again, because at the moment we cannot observe this at the bottom of the mountain. It's too difficult with the tools we have in seismology. We can try to simplify the problem and try to filter these images to the long wavelength, for instance, spherical harmonic 0 to 4. And in that case, what we see is that if you consider some purely thermal models or some thermochemical model with small density contrast between dense and regular material, then we observe some anti-correlation between seismic velocity anomalies and the topography of the core mantle boundary. That is to say, negative seismic velocity anomalies or decrease in seismic velocity anomalies correspond to increase in topography. And of course, that's the other way around for strong thermochemical models, like the one I've shown earlier. In that case, you get some correlation between the filtered between the filtered seismic velocity anomalies and the topography. That is to say, decrease in seismic velocity correspond to also a depression in the core mantle boundary. Again, at the moment we can give some answer from the dynamical point of view, from the modeling, but we don't have answer from observation because it's very difficult to observe this. You have to keep in mind that these are very small topography, 2 kilometers, something like this. Okay, what about seismic attenuation? I mentioned earlier that the rock of the mantle are elastic, which allows seismic waves to propagate through it. It's not exactly true. The mantle is not perfectly elastic, and this is due to some presence of some small defect within a crystalline structure. Well, I won't say more about this, but the key point is that these small defects are inducing some energy loss. Part of the energy of the seismic wave will be dissipated, and this creates, of course, some attenuation of the seismic waves. This is physical attenuation because, of course, as the seismic wave is traveling away from the source, it is also being attenuated, but this is some geometrical attenuation. Here we speak about physical attenuation. We can measure this attenuation with one quantity we call the quality factor, Q. And Q, a large quality factor, Q, means that the attenuation is low, very few attenuation. And of course, low quality factor means high attenuation. In the case of the Earth mantle, it goes from 500 to the quality factor, goes from 50 to 500, and on average, at the bottom of the mantle is around 300. Anyway, the important thing here is that attenuation is a thermally activated process. That is to say, the larger the temperature, the stronger the attenuation. So we can get a hope here to measure the temperature, or to have some idea on temperature and temperature anomalies simply by measuring the attenuation, or actually by measuring simultaneously the attenuation and the shear wave velocity. So this is what we have done here. The first step is to, again, use some seismic data, but this time some waveform data, and to invert this data for two quantities, shear velocity anomalies and quality factor. Second step, we calculate some temperature anomalies from these seismic velocity anomalies, and independently we calculate some temperature anomalies based only on the observed quality factor. So there is a little bit of cooking behind. I will not go into the detail, but the main idea is this: we calculate temperature anomaly from VS, shear velocity, and from Q. And of course, the last step is we compare these two things at one specific place. If the two quantities, the temperature anomalies from VS and from Q at one given place, and for one given assumed structure, thermodynamic structure, are not equal to one another, it means that, or we can interpret this in a, by the fact that the thermochemical structure we assume is wrong. So for instance, if we assume a purely thermal structure, we calculate the temperature anomaly from VS, temperature anomaly from Q, and if these two are differing, if they are not equal, then we can say probably the assumption that we have a purely thermal structure is not correct. So this is what I'm showing here. We checked, or we made some observation for two different regions. One region which is located at the western tip of the Pacific low shear wave velocity province, which is represented here in yellow. This is for shear velocity anomalies. This is for the quality factor. And another region in the North Pacific, which is very close to average mantle, and which is represented here in blue. Okay, so we get some shear velocity, some profile for shear velocity in the lower mantle for quality factor. Now we calculate temperature anomalies. In the case of the North Pacific location, which you remember is close to average mantle, so we expect that there is no big variation here. We see that the temperature anomaly predicted by both data, quality factor and VS, are matching very well. So probably it's purely thermal there. But now we do the same exercise for the western tip of the low shear wave velocity province. Here, the temperature anomaly calculated from quality factor, and here from VS. Plus, in that case, we assume a purely thermal model plus the post-perovskite anomalies, which can be triggered by, you remember, some variation in the stability of post-perovskite. Clearly, at the bottom of the mantle here, it does not match, even if we take into account different sources of error bars, including the activation energy. So we need to add something, and this something is, for instance, iron or composition. If we add some iron, if we assume that there is about 3% iron in these low shear wave velocity provinces, and if we recalculate the temperature anomalies from VS, then we match the temperature anomaly predicted by quality factor, by attenuation, at the bottom of the mantle. So clearly, this kind of exercise shows that these low shear wave velocity provinces are not only hotter than average, probably they are also chemically different. And probably one ingredient is an increase in the fraction of iron, or in the content of iron. So let's leave the geographer with a take-home message. So maybe the most important thing is that seismic tomography shows that there are some large-scale structure in the bottom of the mantle, let's say between 2,500 and 2,900 kilometers, and that these structures are likely hotter and chemically different compared to the rest of the mantle. So if I have time, I would like to introduce the Astronomer. It's also a painting by Vermeer. And at the time, Vermeer, or about a few decades before Vermeer painted this painting, or made this painting, a famous scientist, Galileo, pointed his telescope toward Jupiter, and he saw this, what we call now the Galilean moons. To be very honest, he didn't see what he saw is mostly something like this. But it was very important, as you know, because it really triggered some people to it really pushed people to think about the model of the solar system, and to help people to move from a geocentric system to an heliocentric system. And anyway, these pictures were anyway taken by Galileo, but not Galileo the scientist, Galileo the NASA probe. So what do we know about the structure of these icy moons? A possible structure is that you have a core of rocks, maybe in some cases a mix of rocks and ice, and around this core of rocks, some ice layers of different type of ice. At the top, some ice one layer, so low pressure ice, and probably close to the core, some higher ice pressure. In the case of Ganymede, which is the biggest moon of the solar system, the biggest moon of Jupiter also, you may also have some small core of metal in the center. On the other hand, in the case of smaller bodies like Europa and Pluto, the pressure at the core, at the boundary between the core and the hydrosphere, so the water, is not high enough to support high pressure ice. So we only have a layer of ice, low pressure ice, ice one, and which is surrounding a core of rocks. Of course, the cooling of this body, which means the evolution of the ice layers, is controlled by the heat transfer through the ice layer itself. And if it is big enough or it is thick enough, this layer can be animated by convection again. Maybe I just make one short stop here to say why it's possible to get. You probably have heard about subsurface oceans within icy moons and also within Pluto. How can this be possible? It's actually a consequence of the phase diagram or of the liquidus of the water, which is represented here in blue. Down to about 0.2 gigapascal, so for ice 1, the Clapeyron slope of this liquidus is negative. That is to say, the temperature of the liquidus is decreasing with the pressure. After, for high pressure ices, it is increasing again. So what is happening when the geotherm, that is to say the temperature within or the profile of temperature within this body is cooling down? It's going to go to the left here, and as it goes to the left, you crystallize first some layers of ice at the top and at the bottom, and in the middle here you leave some ocean, some subsurface oceans, etc. So again, in the case of a small body like Pluto and Europa, the core is at a pressure of lower than about 0.2 GPS. So you would only have a layer of ice, then some subsurface ocean, and then a rocky core. Anyway, how can we study this kind of evolution? Of course, we could run some specific model of convection for one specific body and then for one specific parameter, but this is very time-consuming. So another strategy is to do what we call parameterized convection. That is to say, we first run a lot of simulation of convection, which reach steady states. And then we built what we call some scaling laws from this. The scaling laws are relating basically the output properties, for instance, average temperature, the heat flux at the top, to the input properties, which mainly is a Rayleigh number. Right? And in the case of icy moon, it can be also the heating rate within the ice layer. And then we solve the conservation of energy for the radius of interfaces, that is to say the radius, in that case mainly the radius between the ocean and the ice layer. So we solve this energy conservation at each time step. And as I mentioned, this is computationally cheaper than doing some simulation for each specific case. In the case of icy moon, we need to keep in mind two important ingredients. First, temperature of ice depends strongly on temperature, and if you remember the first part of my talk, then you should say A, but then we will have some stagnant convection with some limited heat transfer at the top due to the formation of a stagnant lead. And the second thing is that the presence of internal heating. So of course in the ice, internal heating is not related to radiogenic element, but in some cases, in particular in the case of Europa, also Enceladus, it might be related to strong tides which dissipate some energy within the ice layer. So in that case, if you assemble these two elements, strong temperature dependence of viscosity and tidal dissipation, you get this kind of models, which is not exactly calculated for Europa, because you see that the core of Europa would be much more bigger, much bigger. But typically you see that you get some very hot interiors with some small plumes which are rising from the bottom of the ice layer. And then by doing some parameterized convection models, we can get some interesting information for the evolution of these ice layers. First, we can better understand what is the influence of the internal heating on the evolution of this layer. So this plot is actually showing the thickness of the outer ice layer as a function of time, and you see that it's a logarithmic scale. And of course, it's not really a surprise, but if you increase the internal heating, then it's very difficult to crystallize the ocean, and you get some very thin layers. If there is no internal heating, which is a blue curve here, you can complete the crystallization of the ocean within a few tenths of a million years. But if you have some dissipation, typically around 0.5 to 1 terawatt, which is what is expected in the case of Europa, then at the end of the calculation, or at the end of after 4.5 billion years of evolution, you can expect some layers, thickness of the outer ice shell of Europa around 20 to 40 kilometers. And the second element, which I didn't introduce so far, is the presence of impurities within the oceans, or the subsurface oceans. You can imagine that it is composed of pure water, but actually you have other elements, like for instance ammonia, maybe methane, and other salts. And you perfectly know that if you add some salts in the water, then it's more difficult to freeze the water. So exactly the same effect is happening here. You depress the liquidus, and if you add about 3% of ammonia in volume, then you further oppose the crystallization of the ice layer. Even in the case of where you have no internal heating, the blue curve again, you never complete the crystallization of the ocean. And for typical value of the power in the range 0.5 to 1 terawatt, again, you end up with some thickness of outer ice shell of about 40 to 20 kilometers. Okay, and the last slide is again the Geographer and the Astronomer. Now I put these two slides close one to another to show that if you look at carefully, you will see that it is exactly the same person, the same model. Vermeer planted the same guy in Astronomer and in the Astronomer and the Geographer. Of course, you probably didn't know about this, but for me, it means something very important. It means that because the physics and the chemistry is a priori the same throughout the solar system, then the tools that we use to study the evolution of the Earth's mantle can be used, of course, adapted, but they can be used also to study the interior and evolution of other planets, including icy moons and other rocky planets, and maybe also one day the exoplanets. Okay, so I finished, and thank you very much.
Thank you very much, Professor Deschamps. And any question?
So I think your model, of course, needs some observational data, yes, for the like 3D structure analysis. But what kind of observational data you're using?
So you speak about the tomographic models?
Yeah.
Okay. So the data are travel times of seismic waves. That is to say, when an earthquake is happening, the seismic waves are traveling. We know exactly when the earthquake happened, and we can record exactly the time at which some specific phase, for instance, the S phase, arrived at one seismometer. Okay. If we have one earthquake and maybe 10 or 20 or more seismometers, we will have different travel times. And thanks to this, we are able to when we compare the different travel times, obtain a different station, and for a lot of earthquakes, we can build these tomographic models. So the answer to your question is travel times. Difference in travel times in the propagation of seismic waves. But now we can do even better. We don't use only the arrival of seismic waves. So we don't use only the travel time, but we also use the shape of the wave. So what we call the waveform. So these are the main data that we use for tomographic models. Now tomography or seismology can use other techniques, and I briefly mentioned the normal modes. The normal modes corresponds to some free oscillation of the Earth, which are triggered by big earthquake, for instance. And you have to imagine that the Earth is oscillating like when you hit a bell, you create some oscillation of the bell. So you will create here some oscillation of the Earth with a different sort of or different mode of oscillation, radial, spheroidal, etc. So this is the data we use to do some seismic tomography.
I see. So for the moon model you showed later, what kind of observational data you might actually need?
So it's more complicated this, but some people, in the case of Europa, they are basing their reasoning to calculate the thickness of the crust on purely tectonic features that we see at the surface. And basically, it turns out that when you do this, or basically they calculate the elastic thickness of the ice shell. But when you do this and you compare to models like the one I showed, you get some discrepancy between the two. Typically, the models or which are based on the elastic thickness predict some much thinner layers in a range, let's say 20 to 10 kilometers, while model of parameterized convection are more in the range 20 to 40 kilometers.
But observationally, you can measure such as things.
No, we don't have. Well, there are now some projects for some. The next generation of probe going to Jupiter should bring some maybe a seismometer, but it's not sure, and should bring some instrument to measure the heat flux, and maybe to measure the and some also some instrument to to create some borehole and see if we can. But we won't reach 20 kilometers, even 10 kilometers anyway.
I see. Thank you.
Okay. Any other comments? Any questions? Deschamps?
And I'm just wondering if the rotation is important. Rotation of the planet is important for these.
The rotation of the Earth
Right, right.
is important for. It's very important for the dynamic of the core to generate the magnetic field, because it is what will create the geostrophic column, which stretches the magnetic field in a north-south direction. But for the mantle, it's absolutely not important. We even neglect the acceleration of the mantle rocks. Typically, the value of the velocity, the typical value of the velocity of mantle rocks, of convection, is 1 to 10 centimeters per year. So the Coriolis force has absolutely no effect. You can safely neglect it, if it is your question.
Okay. Any other questions? Comment? Please.
Are the gravity mass of the Earth any help in your models? Like, because I have seen topographic maps taken from space.
The mass of the Earth.
Yeah. Like density maps of
I'm not sure I understand where you want to go.
I was just wondering if it's also used in your models, or it's just the measurements from earthquakes.
We do have a very good description of the radial density profile within the Earth, and also the radial shear wave velocity anomaly within the Earth. But we don't have a measurement of lateral variation in the density. We do have with the normal modes, but it is still controversial because there are still some interaction between the different modes, which makes the interpretation difficult. Some people say we have, most of the people think, and actually the latest model based on normal modes, which shows some lateral variation in density, shows that in this low shear wave velocity province, you get some excess density. And there are very few models which show the other way around. But it is really some research in progress. The latest results show that we get some increase in density. But the radial density, we know that very well.
Okay. Pass up. That's thanks, Professor Deschamps again.
Thank you.